Yeah. So next speaker is Quentin Patet, and he's going to talk about estimation of smooth densities in Wasserstein distances.
Good afternoon, thanks a lot. So yeah, today I'm going to talk about estimation of smooth densities in Wasserstein distance, and this is joint work with John Weed from MIT. So the problem is maybe one of the most fundamental problems in statistics deep down. We have a distribution mu f that has some density, and we see an IID sample from this distribution, and we want to produce an estimate of the density that's close in some distance, right? So we have these points in blue coming from this distribution with a density in red, and we want to produce an estimate of the density. So of course, there's a very wide literature over many, many classes of non-parametric classes of densities for this. And in most results, the difference between the densities is measured vertically, right? So we want these two objects as functions to be close. Here, what we're interested in is producing two objects that will be close in Wasserstein distance, right? So this is something that comes from the problem of optimal transport, right? That goes back many centuries. In optimal transport, we want to transform with a transport function t a certain measure to map it to another one, right? So measure mu to measure nu, and we want to do so by having minimal global effort, right? So this means that looking at all the functions that transform a variable x with distribution mu into a variable tx with distribution nu, we want the one that has the smallest integrated difference between x and tx. Right? And so in particular, this creates a distance between distributions, right? So this Wasserstein distance, WP, that is the objective of this optimization problem. And it allows to compare distributions directly in the sense that if the variables tend to be close, then the distance will be small. And of course, if the two distributions are the same, the distance will be 0. So it measures the smallest metric difference between these distributions. So it allows to do things that are really nice. In particular, if you've got two Dirac masses that are really close, then the Wasserstein distance will be small. And if they are further apart, then the Wasserstein distance will be large, which is not something that we observe with divergences like the KL, maybe. It's also very polyvalent, so we can compare something that's completely atomic and something that's completely continuous, etc. And has lots of application as a loss as well. So this motivates a little bit this question of getting an estimate of WP or of directly mu or nu in this Wasserstein distance. So this has many applications in statistics and machine learning. There's a very nice book by Perret and Couturier about this. And in particular, in statistical learning, two things that can be pointed out are these notions of minimum Kantorovich estimators, so directly using this Wasserstein as a loss, a little bit like the analogy of the KL for maximum likelihood, or to get barycenters of these distributions mu I through this Wasserstein distance. So often, from a statistical perspective, then these distributions mu or mu I are not known, and we have sample access to it. And often what is done is to use directly the empirical measure, right? So this average of all the Diracs of all the observations that can be plugged in directly. Because it's a distance, then the only thing that needs to be understood is the difference between the distance between this empirical measure mu hat n and mu, right? So what's in orange and underlined. And we know that when n goes to infinity, this actually converges, right? But now the more modern question is, what are the non-asymptotic rates? How fast does this converge? And in particular, how fast does this converge in high dimension? So we know that the empirical measure is a bad idea in high dimension in general. This is just because of the size of the space. If we have if we have a certain compact space and we cut it into small cubes of size n to the minus 1 over d, we have n little cubes. And so this means that when we have n points in it, a large fraction of them are going to be empty with high probability. And now because we need to transport a point to some neighboring cube, it takes us at least n to the minus 1 over d in distance. This is why we have a very slow convergence for the empirical distribution of order n to the minus 1 over d in high dimension. So the question is, can this be improved for regular measures, and in particular measures with some density that's smooth? So on the other side, in statistics, there's a large literature around these ideas with wavelet approaches for estimators or with kernel density estimators. And the general message is that the more smoothness you have, the better your estimation rates are. But it's not focused at all directly on the empirical distribution. In this sense, it wouldn't really make sense. We're focusing directly on the density. It's more focused on information theoretic questions of how hard is it to estimate a density. In this work, we follow this point of view. So we have an estimator that's based on a wavelet decomposition. And what we obtain is that when we have a function f with Bezov smoothness s and bounded below by L, which is not something that comes up often in density estimation, we have these improved rates. And in particular, in high dimension, what's interesting is this n to the minus 1 plus s divided by d plus 2s. It interpolates nicely when s goes between 0 and infinity, between 1 over d, which is the worst case when there's no smoothness, and 1/2, which is the parametric rate when the smoothness is almost infinite. Without boundedness below, there's an additional factor 1 over p that we also understand, and it's related to some previous work on estimating with integrable probability metric. However, so one issue with our estimator is that it's based on a wavelet decomposition and then on a projection on the space of distributions, so it doesn't come with a nice representation to do computations with. And so now we have this sort of tension between, on one hand, these atomic distributions, like the empirical distribution, that give you nice tractable problems, but are worse statistically, and density estimation with estimators that have optimal statistical performance, but no general algorithm to compute the distance or optimize it. So what we do is we say here that we have this density estimator that's better statistically. What we can say is we can forget about the initial points, and we can resample from this estimator, right? So we can resample capital M points, as many as we want, potentially much larger than n, and then we consider this estimator of the measure. And this is something that we can do computations with, and it's based on a density estimator. Now, more generally, for any estimator that we have that has an improved rate that's not in n to the minus 1 over d, but n to the minus some gamma divided by d for gamma larger than 1, what we can do is we can have this resampled estimator, and we can control its precision by decomposing the error into the sampling and resampling error. The second term has an error of order capital M to the minus 1 over d in high dimension, and we control capital M. We can make it equal to the second term by taking capital M to be of order n to the power gamma. Now, on the other hand, this means that we have a problem, an optimization problem on capital M points. We understand how the Wasserstein distance can be approximated up to some precision with up to some precision epsilon. We can understand its complexity in terms of capital M and epsilon. And so what our final result tells us is that we can get an estimate with precision n to the minus gamma over d, when gamma can be greater than 1, with a running time that depends on gamma and depends also on p and d. And the nice thing here is that we control gamma, and so we can buy more statistical precision, and we know how much we lose on the computation side. And so if you have more questions, the poster will be 177 tonight. Thank you very much.
Any question while the next speaker sets up?
We hope that it's possible, but we haven't done so far. I'm sorry, why does the? I'm sorry, I couldn't hear you. Because we have to reproject on the space of distribution. The first thing that we create is not necessarily a distribution. It can become negative. It doesn't integrate, might have issues integrating to one, etc. It might not be in base off in the right way we want. So this is why there's some issue with projecting again.